People say life's too short, live it to the full. There's only a fine line between life and death. Do you fear any of these things? Dying from a snake bite, being killed by a shark, being struck by lightning? Well, if you don't live at the sea, you don't go swimming in the sea, then you probably don't fear being attacked by sharks. But many who do swim in the sea are terrified. Also, many people who live in rural areas or even semi-urban areas have a fear of being bitten by a snake. But just how likely is it that one of these things will happen to you? Probability can help us consider our chances. Mr. John Paxton is a shark expert with the Australian Museum in Sydney. Here's what he had to say about the risk of being bitten by a shark. Statistics show that over the past 30 years, sharks have killed only 31 Australians. This compares with 250 who die each year crossing the road. In other words, there's a bigger chance of dying on the roads getting to the beach than being attacked by a shark in the water. The risk of a shark attack is virtually nil. What about the chances of dying from a snake bite? Let me quote you from South African research. In South Africa, over 10,000 people are killed every year in road accidents. 2,000 die from lung cancer and other diseases related to cigarette smoking. About 200 are struck and killed by lightning, and fewer than 20, perhaps as few as 10, die from snake bite. These are annual statistics. Out of all the deaths in South Africa each year, thousands die on the road and from smoking. A couple of hundred are struck by lightning, and only a handful die from snakebite. Makes you think. We have much more chance of dying from car accidents or smoking-related diseases than from snakebites. So we should be more concerned about road safety and the dangers of smoking than fearing snakes. In this lesson, we're going to look at the probability of something happening and compare driving safely with probability of that event not happening. By the end of this lesson, you should be able to explain why the probability of any sample space is always 1 and calculate complementary events. I want to start out by bringing in someone you should all recognize by now. Hi, Gerard.
Hi.
I want to start off this lesson with the weather.
Okay.
The weather forecast for tomorrow is 80% chance of rain. What chance is there that it will not rain?
That's easy. 20%. Because it can't be more than 100%, right?
Correct. As simple as that is, it's an important concept in probability. The chance of something happening can't be more than 100%. Here's another example. Here's a pencil bag with pens inside. It contains 4 blue pens, 1 black pen, and 1 red pen. I'm going to put my hand into the bag without looking and pull out a pen. What chance do I have of pulling out a blue pen?
Okay. There are 6 pens in the bag, so they all have an equal chance of being pulled out.
Correct. So that's the sample space.
And the total number of possible outcomes is 6. 4 of them are blue, so the number of favorable outcomes is 4.
Good. And we call the number of favorable outcomes the event space. The probability of getting a blue pen is the number of favorable outcomes out of the number of possible outcomes.
That's 4 out of 6. Or we could even say 2 out of 3.
Great. Now, what's the chance of pulling out a pen that's not blue?
The sample space is still 6, but if the pen isn't blue, it can only be the 1 black pen or the 1 red pen. That means it can be one of 2 pens. So, the chance of pulling out a pen that's not blue is only 2 out of 6.
Right again. Now have a look at this. If we add together the probability of getting blue and the probability of not getting blue, what do we get?
4 6 plus 2 6 is 6 6, and that's just 1.
Exactly. In other words, the probability of an event added to the probability of that event not happening is 1. Here's another example. Take a look at this dartboard. What's the probability of throwing a dart inside a circle?
Always assuming I can actually hit the dartboard.
Well, let's assume we only consider throws you manage to land on the dartboard. What's the probability of throwing a dart inside a circle?
Well, wherever the dart lands, it will be inside a circle. So, there's a 100% chance of landing in a circle.
Well done. The number of favorable outcomes is all the possible outcomes. The sample space, which is the whole board, is also the event space. So this gives you a probability of 1. Another thing follows from this. The number of favorable outcomes in an event can never be more than the number of possible outcomes. So 1 is the highest probability we can ever get. Now, what is the probability of my landing in a blue section on this dartboard?
That's easy. It's 0, because there isn't a blue section.
Exactly. So the event space is 0 and the smallest probability we can get is 0. We've just seen two things here. First, the probability of the whole sample space is always 1. We write it like this. The P is for probability, as usual, and the S is for sample space. Second, the probability of any event, the E here stands for event, must be 0 or 1, or any number between 0 and 1. In other words, the probability of an event is greater than or equal to 0 and smaller than or equal to 1. This fits with a probability scale which ranges from 0 to 1. The probability of an event falls between 0 and 1. Now let's have a look at complementary events. In our example with pens, we said that the chances of pulling out a blue pen are 4 out of 6, and the chances of pulling out a pen that is not blue is 2 out of 6. So the probability of an event added to the probability of that event not happening is 1. These two events are called complementary events. Complementary events are events which, added together, give us a probability of 1. Another way to say this is that complementary events make up the whole sample space. Here is a probability statement to show that the probability of an event happening added to the probability of it not happening is 1. The E stands for event, but we could have used any other letter there. An event not happening is called the complement of the event. Notice that's complement with an E, not an I. So the probability of an event plus its complement is equal to 1. Now, can you use the statement to work out the probability of the complement of an event?
Can I treat this like an equation?
You're absolutely right, you can.
So, I subtract the probability of the event from both sides. That means the probability of an event not happening is equal to 1 minus the probability of the event.
This makes it easy to work out the probability of the complement of an event. If we know the probability of the event, we just have to subtract the probability from 1. Here's a calculation to work out. What is the complementary event of throwing a 6 on a dice?
It's not throwing a 6.
Yes. And what's the probability of throwing a 6?
It's 1 out of 6. That is 1/6.
Okay. Now, what's the probability of not throwing a 6?
That's easy. It's 1 minus 1/6, which is 5/6.
So it's much easier not to throw a 6 than to throw a 6. But that's true for any number on the dice, not only 6. What's the probability of throwing a 3?
Again, it's 1/6.
And the probability of not throwing a 3 is
1 minus 1/6, which is 5/6 again.
In other words, some ideas happen in people's minds because they're not comparing similar things. We need to compare the probability of throwing a 6 to the probability of throwing each of the other numbers. This will give us the same probability each time. We can't compare the probability of throwing a 6 to its complement. In this case, the complement happens more often than the event.
Wow. It really makes you think. Next time I hear someone say that the chance of something happening is high or low, I'll check what it is being compared to.
An excellent point. We need to bring more mathematics into our thinking. Now, let's review what we've done today. We've looked at two rules of probability. The first rule is that the probability of any sample space is always 1, and a probability can never be less than 0 or greater than 1. This leads to a second rule, which is that the probability of something not happening can be calculated by subtracting the probability that it will happen from 1. These two events are called complementary events. This means that together they cover the whole sample space. Now, here's something for you to do for this week's task. In a motor race, there are 7 teams. Each team has 2 cars in the race, and each car has an equal chance of winning. Write a probability statement for Team A's chance of winning the race. Then write a probability statement for Team A's chance of not winning, and use the statement for a complementary event. That brings us to the end of today's lesson. Until next time, have fun with the task.